Hello, welcome to my final project updates on the interphase effects on nanocomposites. My name is Andres Hassun. I am an undergraduate student at the Cockrell School of Engineering at the University of Texas at Austin. Before we begin, I'd like to acknowledge Dr. Pavan Kaloru and Suzanne Peterson for mentoring me during this project, as well as the Texas A&M online O-REU program, Texas A&M High Performance Research Computing Center, and the Center for Research Excellence on Dynamically Deformed Solids, or CREDS. This work was supported by the Department of Energy, National Nuclear Security Administration under award number DE-NA0003857. Let's begin with an overview. First, I'll introduce my topic, go into some literature review, and then the mechanical setup for the simulations I ran. Then we'll get into the results of these simulations with varying interphase properties, and then we'll conclude and see what the next steps are. So the interphase is a component of nanocomposites. It is a graded region surrounding the particle in which material properties differ from the far-field matrix, but this has not been heavily studied in the past. What occurs is that polymer chains close to the particle experience different boundary conditions than those far from the particle, thus creating different properties along a gradient. The span of the interphase is estimated to be on the order of tens to hundreds of nanometers, but we actually don't know how far it spans as it has been researched heavily. Finally, the interphase has increased significance at larger particle surface to volume ratios. So when a particle is smaller, the surface area is higher relative to the volume, and so the interphase has more significance. So some of the applications of studying the interphase region is that we can create stronger and tougher materials. Large deformation is important to study as the material is stronger if only the particle carries the load, but will fail if the interphase debonds between the particle and the matrix. The interphase region is critical in controlling a lot of the properties when undergoing plastic deformation. So we aim to look into plastic deformation, while previous studies has mostly focused on elastic deformation. The images you can see here are from a study where they reinforced the interphase with carbon nanotubes. This allowed them to carry more load per displacement, thus creating a stronger material. We'll be using FEA analysis in our research. This has been previously used by other studies looking into the interphase region, such as when they used the AFM technique to experimentally find interphase gradient data at specific points. As you can see in the middle graph here, they compared their experimental and FEA data of the AFM test, as well as on the right, they compared their FEA data with and without an interphase gradient to deconvolute the stress concentration from the interphase properties. However, our experiment will be using tensile tests instead. Some previous work that has been done by the O-REU group on this topic is on the left we can see a schematic of the deconvolution of stress concentration from interphase effects. So we can see the blue line here, which is the FEA data without an interphase, needs to be subtracted from the red line, which is the FEA data with an interphase, in order to get to the black line, which is what we expect to find in an experiment. However, this is more of an estimate and may not be what we find in actuality. On the right, we can see the sort of tests they performed. They used a circular particle while applying tension to the right in order to get the data shown in the middle figure here, which is the normal stress in the XX direction versus the global strain with an interphase gradient. Now, for my simulation, we used a rectangular alumina particle surrounded by a polycarbonate matrix. A rectangular particle is modeled for consistency and ease of data manipulation, as a rectangle has points all lined up on the same axis along its edges. On the right side, we have a tensile load ramping up over the course of 1 second linearly from 0 micronewtons to 10 micronewtons. In order to get the measurements, we have 4 regions surrounding the particle. which comprise the interface, and each one spans a width of 50 nanometers. Speaking of measurements, we averaged 21 different points at each measurement site. Each point was separated by 25 nanometers, spanning a total of 500 nanometers across all points. Each interface region, additionally, as well as the far-field matrix, contained a measurement site, which was centered along the perpendicular axis. So it's right in the center of each region. Now let us get into our data. First, we have our control condition without an interface. We do have different numbers regions here. These are the same regions which we will be using when we do have an interface. So it's the same location for gathering the data points. All of the regions have the same Young's modulus, yield strength, and tangent modulus. And we can see that the 4 regions we looked at are very close in terms of their normal stress versus global strain, while the bulk is slightly less than all of those. This is expected due to the stress concentration. Here's the same graph, but on the right side here, we have a zoomed in portion of the elastic region. So we can get a better look at that, and we can see that they are still very close. These are all in the x direction, by the way, the xx direction. Now we move on to the yy direction, again with no interface, and we can see that all of the stress being put in this direction is due to Poisson's ratio. So it's much lower than that in the x direction, but there is this sort of jump here around between 2 and 10 megapascals. This we'll get into later, but it seems to become less severe when we start adding more regions. Now we have our 2 times the modulus of the interface, so the peak condition of the interface region is 2 times the modulus of the bulk. We can see that each region starts having its own distinct sort of line in the graph, and we can get a zoomed in portion here of the elastic region, and again we can see that there is separation between these lines as there is an effect going on other than the stress concentration. Now onto the yy direction of this 2 times modulus interface. We can see that the jumps here are still there, but they're less severe than that of having no interface. Now we have 5 times the interface modulus over the same distance. So this is the same number of region where the properties drop off much faster and the peak properties are higher. So we can see that under these same conditions, the first and second interface region never actually reach their yield strength, while the third and fourth and bulk do reach their yield strength and then taper off into their plastic deformation regime. On the right here, we do see a bit more of that earlier portion. However, this is more zoomed in to highlight the up and down effect that occurs on the first through fourth interface region. Onto the YY direction. Again, we're seeing this jump as previously, but it is getting less and less severe. Before we move on, we're going to talk about the measurement for the 5 times interface modulus with a similar slope as the 2 times interface modulus. It is the same measurement technique, but it is extended across 8 regions, where each region still spans 50 nanometers. For these regions, the peak properties are higher, but they drop off at a similar rate as the 2 times interface modulus. As for the result, we can see that each region has its own distinct line, which seems to evenly disperse down all the way to the bulk. Now let's look at the zoomed in portion of the elastic region. We can still see that each region has its own distinct curve. In the YY direction, we don't see these sort of jumps at the beginning here. It's much, much smoother. This may be due to an increased number of regions, and more tests will have to be run with this number of regions to confirm it. So, to conclude, understanding the effects of the interphase region can lead to the creation of stronger and tougher materials. FEA simulations are a valid method to supplement experimental data and to deconvolute stress concentration and interphase effects. We surround a rectangular alumina particle with a polycarbonate matrix. Around the particle are regions of varying moduli to simulate the interphase. With the interphase, we see a different trend between each region. We need to look at the trends without an interphase to properly deconvolute the stress concentration. By varying the modulus, we can evaluate different effects of the interphase and see how each one compares to experimental results. And next, FEA simulations should be run varying Poisson's ratio as well as moving into 3D models. Thank you for listening to my final project update, and I hope you have a nice day.